In this episode, we step into the world of controls, which is the practical heart of governance and assurance. A control is a safeguard that prevents harm, detects problems early, or limits impact when something goes wrong. And in AI systems, controls must address risks that are different from ordinary software risks. For brand new learners, it helps to think of controls like the rules and procedures in a school that prevent cheating, detect cheating, and respond when cheating is discovered, because you need more than trust to keep the system fair and reliable. AI-specific controls exist because AI can behave unpredictably in new conditions, can drift over time as data changes, and can cause people to overtrust outputs that sound confident. Controls also exist because AI systems often depend on data pipelines and model artifacts that can be altered, intentionally or accidentally, in ways that change outcomes without obvious warning. Evaluating the design and effectiveness of these controls means asking whether they are well chosen for the specific risks, whether they are built into real workflows rather than living on paper, and whether evidence shows they work in practice. This episode is not about listing every possible control, but about teaching you how to reason about control design and how to tell the difference between a control that looks good and a control that actually protects people. Task 12 expects an evaluator to look for both design quality and operational effectiveness, because a control that is beautifully described but rarely used is not a control, it is a story. By the end, you should understand what makes a control AI-specific, how controls map to real risk, and how evaluators validate that controls actually function over time. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. AI-specific controls start with understanding what makes AI risk unique. Traditional software usually follows explicit rules, so failures often come from coding mistakes or missing logic. AI systems learn patterns, so failures often come from training data limitations, changing input distributions, and the model's tendency to generalize beyond its experience. Another AI-specific risk is automation bias, where humans defer to the model even when it is wrong, because it feels authoritative. There is also the challenge of explainability limits, where the model cannot always provide clear reasoning, which affects accountability and the ability to contest decisions. These risks imply control needs that go beyond normal access control and patch management, such as controls for drift detection, controls for human oversight triggers, and controls that ensure model updates are tested and approved. For beginners, an easy way to understand this is that AI is not just a program you can read. It is a behavior system that changes with data and context. Therefore, controls must be designed to manage behavior, not just manage code. Evaluating controls begins with mapping which risks are plausible in the specific use case, because the best control is the one that targets a realistic failure mode. If the organization designs controls without a risk map, it often ends up with generic controls that miss the most likely harms. Control design quality depends on clarity, meaning the control has a clear purpose and a clear mechanism. A vague control might say we review the model regularly, but that does not tell you what is reviewed, how often, by whom, or what happens if issues are found. A well-designed control is specific enough that two different people would interpret it similarly and could demonstrate whether it was performed. For example, a drift control might specify which input features are monitored, what thresholds indicate abnormal change, and what escalation steps occur when thresholds are exceeded. Design quality also depends on scope, meaning the control covers the assets and activities that truly drive outcomes, not just the most visible parts. If an organization controls model files but does not control data pre-processing changes, it may miss the biggest source of risk. Beginners should remember that a control is only as good as its connection to reality. If it is designed around the wrong part of the system, it can be rigorous and still irrelevant. Another design quality feature is proportionality, meaning the control intensity matches the risk, because over-controlling low-risk systems can create busy work, while under-controlling high-risk systems creates unacceptable exposure. Evaluators look for controls that are tailored, not copied, because copied controls often do not match the use case. Effectiveness is different from design, because a control can be perfectly designed and still ineffective if it is not executed consistently. Effectiveness is about behavior in the organization, not just words. To evaluate effectiveness, you look for evidence that the control is actually performed, that it produces useful signals, and that it leads to action when needed. For beginners, imagine a rule that students must submit assignments through a plagiarism checker. It is effective only if submissions actually go through the checker and if the school responds appropriately to results. In AI systems, effectiveness evidence might include logs showing that monitoring ran, tickets showing that alerts were investigated, records showing that model updates were reviewed, and documentation showing that incidents led to remediation and retesting. Evaluators also look for timeliness, because a control performed late may not prevent harm. For example, reviewing fairness impact quarterly may be insufficient if the model makes high-impact decisions daily and drift can happen quickly. Another element is resilience, meaning the control works under pressure, such as during a production incident or a deadline-driven release. Effectiveness requires controls that are not only defined, but embedded into tools and processes that people actually use. A helpful way to reason about AI-specific controls is to group them by what they do, even if you never use a bullet list to describe them. Some controls prevent harm by restricting actions, such as requiring approvals for model promotion, limiting who can change configuration, or enforcing separation of environments. Other controls detect harm by monitoring behavior, such as drift detection, performance tracking, and alerts for unusual output patterns. Still, other controls limit impact by enabling safe fallback, such as routing uncertain cases to humans, enabling rollback to a known safe model, or narrowing scope when risk rises. Evaluating control design asks whether the organization has a balanced set across prevention, detection, and response, because relying only on one category leaves gaps. For example, prevention controls can fail due to human error or emergency bypass, so detection and response controls are needed as backstops. Detection controls without response are weak because they create awareness without protection. Response controls without detection are weak because they rely on discovering harm through customers or accidents. Beginners should see this as layers of safety, like seat belts, airbags, and traffic laws working together, because any single layer can fail. An effective AI control environment has layered safeguards that reflect realistic failure modes. Human oversight controls are a category where AI-specific risks are particularly obvious, because AI systems can sound confident even when they are wrong. Human oversight controls include triggers for escalation, requirements for review and high-impact decisions, and processes for documenting overrides and learning from them. Evaluating these controls includes checking whether oversight is meaningful, meaning humans have enough context to make good decisions and enough authority to override or escalate when needed. It also includes checking whether oversight is sustainable, because if humans are asked to review too much, they become overwhelmed and oversight becomes shallow. For beginners, this is like having a teacher review every homework problem for every student. It sounds safe, but it is not practical, and it would lead to rushed review. Good oversight controls are risk-based, focusing human attention where it provides the most value. Evaluators look for evidence that oversight triggers catch the right cases, that reviewers are trained, and that decisions are recorded so patterns can be detected. They also look for whether the organization monitors for automation bias, such as reviewers rarely disagreeing with the model even when errors exist. An oversight control is effective only if it changes outcomes when needed, not merely if it exists as a policy. Data and pipeline controls are another AI-specific area, because data quality and transformation choices strongly shape model behavior. Controls here can include data validation checks, feature definition governance, and monitoring for pipeline changes that could alter inputs. Evaluators check whether the organization has identified critical data fields and created controls that detect missing, stale, or implausible values before they reach the model. They also look for evidence of controlled changes to pre-processing steps, because unreviewed pre-processing changes can introduce bias, degrade robustness, or break reproducibility. For beginners, it is like measuring ingredients before baking. If someone changes the measurement without telling anyone, the cake changes, and you may not know why. Pipeline controls also include access restrictions and logging for who can modify training or deployment pipelines, because pipelines are powerful levers for altering outcomes. Effectiveness evidence might include change logs, review records, and monitoring alerts tied to pipeline integrity. If pipeline controls are weak, the organization can lose control even if the model artifact is protected, because the artifact is produced by the pipeline. Evaluating these controls is about verifying that the organization governs the flow from data to model to decision. Model lifecycle controls cover how models are trained, validated, approved, deployed, monitored, updated, and retired, and they are AI-specific because models evolve over time. Controls include versioning, reproducibility evidence, test requirements, approval gates, controlled rollout, and rollback readiness. Evaluators check whether each stage has clear criteria, because vague criteria lead to inconsistent decisions and risk acceptance by accident. For example, a release readiness control should specify what testing evidence must exist, what fairness and safety thresholds must be met, and who approves. Effectiveness evidence might include records showing that models were rejected or delayed due to failed tests, because the ability to stop a release is a sign that controls are real. Beginners should understand that a control that never blocks anything might be ineffective, especially in complex systems where some failures are expected. Another key control is monitoring after deployment. Because models can drift, evaluation checks whether monitoring is tied to triggers and to actions like narrowing scope or retraining. Lifecycle controls also include decommissioning and data cleanup, because leaving retired models accessible can create shadow usage and risk. A strong lifecycle control environment proves the organization can manage models as living assets, not as one-time projects. Evaluators also need to examine control interactions, because AI control environments can fail when controls contradict each other or when one control creates pressure that undermines another. For example, a strict performance target might push teams to tune thresholds aggressively, which could worsen fairness or safety, and if fairness controls are weak, the imbalance persists. Another example is an emergency change pathway that allows rapid action, which is necessary, but if it lacks post-emergency review, it can leave permanent holes in access control and configuration discipline. For beginners, control interaction is like a household rule that says no snacks before dinner, but also says you must clean your plate. The interaction can create unhealthy behavior unless the household thinks through how rules work together. Evaluators validate whether the organization has governance forums or review processes that consider trade-offs across controls, rather than optimizing one area blindly. They also check whether the organization tracks control exceptions and analyzes patterns, because frequent exceptions can signal that the control design does not fit operational reality. A mature organization adjusts controls so that compliance is achievable and meaningful, not so strict that people work around it. Effectiveness includes the control culture, meaning how people treat controls under pressure. A common beginner misconception is that controls are mainly for compliance and do not affect real outcomes. In AI systems, controls directly shape whether customers are harmed and whether incidents occur, because controls decide whether unsafe outputs are blocked, whether drift is noticed, and whether updates are released responsibly. Another misconception is that controls only need to exist at launch, but the most important AI risks emerge over time as data shifts and systems are reused. This is why evaluators look for control durability, meaning controls continue to operate as the system evolves and as teams change. They also look for measurement of control effectiveness, such as metrics about alert response times, override rates, and incident recurrence, because controls should be managed like a system, not assumed to be perfect. Beginners should also understand that controls can fail quietly when they are too manual, because manual tasks are forgotten or rushed, especially when staff turnover occurs. Effective controls often include automation for enforcement and logging, but automation must be governed so it does not create new blind spots. Evaluating controls is therefore partly about realism. Are these safeguards likely to be performed consistently in this organization under real conditions? A control is only effective if it survives ordinary human behavior. To make this practical, imagine an AI system used to route customer complaints. and the organization claims it has strong controls. An evaluator would examine whether model updates require approval and test evidence, whether data pipeline changes are reviewed, and whether monitoring detects abnormal shifts in denial or escalation rates. They would also examine whether human oversight triggers route uncertain or high-impact cases to trained reviewers, and whether those reviewers can override decisions and document why. They would check whether access to model artifacts and configuration is restricted and logged, because unauthorized tweaks could change outcomes. They would validate whether a rollback plan exists and has been practiced, because if harm appears, the organization must be able to limit impact quickly. They would also look for evidence that controls have actually prevented harm, such as records of halted releases, resolved alerts, and lessons learned from incidents. This example shows that control evaluation is not abstract. It is about verifying that safeguards exist at the points where risk enters the system. A well-controlled system is one where a single mistake does not silently become a widespread customer problem. When you step back, evaluating the design and effectiveness of AI-specific controls is about proving that the organization has layered safeguards tailored to AI risks and that those safeguards work in daily operations. Design evaluation checks whether controls are clear, risk-based, scoped to the real levers of behavior, and balanced across prevention, detection, and response. Effectiveness evaluation checks whether controls are executed consistently, produce actionable evidence, and lead to timely intervention when signals indicate risk. It also checks whether controls remain durable under stress, whether exceptions are managed and learned from, and whether control interactions are considered so one safeguard does not undermine another. For brand new learners, the central takeaway is that trustworthy AI is not achieved by a single model score or a single policy document. It is achieved by controls that shape behavior over time, catching problems early and limiting harm when surprises occur. Task 12 expects you to look beyond claims and examine evidence of real control in the system's life cycle. If you can explain what makes controls AI-specific and how evaluators judge both design and effectiveness, you are building the ability to assess whether an organization is governing AI responsibly in the ways that matter most to people and outcomes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.